So, you're here to learn about what a star is. Astronomers often struggle to properly define different bodies within space and often create very vague definitions. For example, astronomers can't really pin the tail on the donkey when it comes to defining a moon, of all things, but simply, we have a simple definition of a star. A star is a massive body of celestial gas which performs nuclear fusion within its core. So that means a star must have a minimum temperature of 10 million Kelvin within its core to perform hydrogen fusion. Additionally, a star should at a minimum have a mass 75 times larger than the mass of Jupiter. The smallest star ever discovered was about the size and still performed hydrogen fusion within its core. Anything smaller and cooler than that would likely be classified as a brown dwarf. Today I'm going to focus on the life cycle of a star like our Sun. Stage 0 is kind of just something I decided to throw in to show what exists before a star begins to form. Well, what is it? Well, before anything else happens, a large body of gas and dust, called a dark dust cloud, kind of just exists in space. Once this dark dust cloud receives a trigger, it will begin to rotate and spin. These dark dust clouds, a type of nebula, have a huge mass and a very low temperature of about 10 kelvins. Now you may be asking, what are the triggers for this process to spark? Well, supernova explosions, calm star death, collisions between galaxies, and the movement of spiral arms within a galaxy can cause this rotation to occur. Stage 2 is when the fun begins to happen. This spinning dark dust cloud may fragment into smaller pieces if spinning fast enough. If these pieces have at least 1 trillion particles per cubic meter, they will likely form a star. If these pieces aren't big enough, they can form a brown dwarf. Now the center of this nebula begins to heat up due to the rotation and amasses a temperature of about 100 Kelvin. Stage 2 is considered the beginning of a protostar's formation. Over this time, this fragment will begin to condense until it is about the size of our solar system. The core of this nebula will be about 10,000 Kelvin. Due to the core's temperature, the star won't collapse in on itself due to rotation and increased gravity. This starts the formation of a star's shape. Moving on, stage 4 is when the fun really begins to happen. A protostar in stage 4 now has a core temperature of about 1 million Kelvin and is mostly shaped, though that cloud of particles still lingers largely around the protostar. Notably, planets begin to form during this stage. Additionally, our protostar is now large and hot enough to barely enter the HR diagram. During stage 5, a protostar will shed that cloud of gas by strong solar winds, which will begin during this stage. Stage 5 protostar will have a temperature of about 5 million Kelvin and is about 10 times the size of our Sun. We're now on our way to the main sequence. Now, our protostar is officially a star as it enters stage 6. It's nearly on the main sequence and has begun fusing hydrogen within its core with a core temperature of about 10 million Kelvin. We officially have a true star. Our star, after some time, will reach stage 7 and is now officially mature and adult, now landing smack dab in the main sequence. For a star like our Sun, a yellow dwarf, it'll likely hold a stellar temperature, usually about a G in the rating, and should have a luminosity and mass somewhat similar to our Sun. Our star will also have hydrostatic equilibrium, which balances out gravity inwards and pressure outwards. Our star can stay on the main sequence for over 1 billion years. Now, after our star has been on the main sequence for a long time, the hydrogen within its core will begin to exhaust itself and run out. This is because nuclear fusion within hydrogen causes it to form helium. This is stage 8. Our core is now entirely helium at this point, and our star just isn't hot enough to fuse helium. So the gravity begins to win, condensing the star's helium core. This in turn causes the star's core to begin to heat up as it condenses. This causes the helium in the layers closest to the core to begin to fuse, and the star's layers begin to expand as a result. This expansion of layers causes our star's surface to cool a bit. Our star gets brighter and officially leaves the main sequence, transitioning into a subgiant. In stage 9, our star's helium core will now continue to contract, repeating the process shown in stage 8, eventually causing the star to achieve significant expansion as the inner layers begin to fuse hydrogen more rapidly. On the HR diagram, there's almost a vertical movement up from stage 8 to stage 9 due to this rapid expansion. At stage 10, our star is now officially hot enough to fuse helium. After reaching a core temperature of about 100 million Kelvin, our star can now fuse helium. Through something called the triple alpha process, 2 helium atoms will fuse to form beryllium, and then fuse again with another helium atom to form carbon. In stars like our Sun, which are considered low mass, this helium fusion causes the core to become degenerate. This makes the core begin to expand in response to this pressure, causing helium flashes, which end up releasing a large amount of energy, which causes this core to finish expanding and stabilize. Compared to stage 9, our star has an almost horizontal movement to the right on the HR diagram from stage 9 to stage 10. Finally, at stage 11, we have a red giant. Our core has burned through all of its high helium and is now entirely carbon. In stars like our Sun, we will never achieve a temperature high enough to fuse carbon. Our inner layers are now entirely helium, while our outer layers fuse hydrogen. Our star has a ginormous radius, potentially having a radius 100 times larger than our Sun. Star death is very near at this point. Alright, at stage 12, at this point, our inner core of our carbon begins to almost idle, just kind of hanging out. The outer core continues to be active, fusing whatever is left of helium at the edges of the core. Our star is now extremely unstable due to frequent helium flashes, eventually sending out our star's layers out into space. These layers won't depart from the star completely and instead stick around for a while, forming a sort of envelope around the star called a planetary nebula. This is caused by our core ionizing parts of this cloud around our star through the use of ultraviolet radiation. A planetary nebula isn't really a nebula in terms of having the ability to birth stars, and more so gets its name from its size of about our solar system and its similar appearance to a nebula. After some time, cooling occurs, and our star's outer layer begins to slip away into interstellar space. These shredded layers can act as a trigger for star formation, even though it's not as effective as more violent star deaths seen in larger stars. Alright, in stage 13, at this point, our star is really only a carbon core. The outer layers are gone. It's incredibly dense and hot, maintaining a super strong gravity. This is now called a white dwarf, and it is still in the HR diagram, but is considered a stellar remnant or a dead star. Evolution is officially over for our star. If a white dwarf is in a mass transfer binary system, it can cause a supernova after reaching the Chandrasekhar mass of 1.44 solar masses. This supernova can serve as an effective trigger for starbirth and will lead to the formation of a neutron star, a small, city-sized object which can emit electromagnetic radiation and spins incredibly fast. If spinning fast enough, it is called a pulsar. From there, a neutron star could form a black hole if the conditions are met for a black hole to form. Usually, the neutron star would need to be in a binary with another neutron star, or would have to still be in a mass transfer binary even after the original supernova. So, that can still happen. However, usually a white dwarf's evolution is completely over at this point, unless some conditions are met, like being in a mass transfer binary system. At stage 14, we are officially back off the HR diagram. The white dwarf has maintained its shape and size, but it has cooled and faded, losing luminosity and really any ability to see the star. Our star is now considered a black dwarf and has a temperature of near 0 Kelvin. It's just a cool sphere of carbon floating through space. Black dwarfs are considered theoretical because the task of locating one is nearly impossible due to the low temperature and small size. However, they are theorized to be the final result of a star like our sun's life cycle. The end.